All right, well, I want to continue on with scripting. So I remind you that we talked about variables, or sometimes called properties, places to hold data. We have functions or methods, which is some encapsulated piece of code, and we have classes, which are collections of functions and variables, sometimes called a data type. Um, the Unity C# has the kind of standard data types, integer, float, Boolean, but it also has some of its own specifically designed for Unity data types. And in particular, an example is the vector3. And there are also 2 vectors and 4 vectors. And the vector3 has a constructor. Vector3 POS is a new vector3 with its X, Y, and Z values in here. I will note that if you don't put an F after a float, it'll throw some kind of error. So that F is required for a float. Now, the vector3 is actually a struct used in Unity to represent positions. These would be points in space, or directed line segments, which are line segments in a particular direction with a particular magnitude, but they don't have any specific location. So this vector3 POS that I've defined to be a new vector3 of 1, 2, and 3, we can access the individual components with a .x, a .y, or a .z. Or we can use the more standard square bracket 0, 1, and 2 to access those 3 components. Another property of the vector class is the dot normalized, which yields a vector in the same direction, but now with a unit length. So it reduces the length or expands it. We also have 2 other properties, magnitude and square magnitude, that yield the length of the vector and the length squared of the vector. Often when we don't really care about the exact, the absolute magnitude of a vector, we only care about relative magnitudes, we can use the square magnitude, which saves on doing a square root calculation, somewhat expensive. There are a number of static properties as sort of named constants. The vector3.0 is all zeros, 0, 0, 0. Vector3.1 is 1, 1, 1. Forward is in the z direction. So forward is 0, 0, 1. And we have the analogous dot back, which is 0, 0, minus 1. We have up, which is in the y direction, so 0, 1, 0, and it's analogous down. And we have right, which is in the x direction, 1, 0, 0. You might notice this is a left-handed coordinate system. Right crossed into, I have to do it with a left hand. Right crossed into y is z in the forward direction. So it's a left-handed coordinate system. There are lots of methods for the vector3, things like the angle between from and to, cross product, dot product, min, max, move towards, normalize, reflect, rotate towards, scale. Lots of different methods. And I'll remind you that our help menu here for the vector3 shows us this is in the scripting reference, shows us all the different properties. Here are those forward, back, up, down, right, left. We have here the magnitude, square magnitude normalized, the different swizzles, .x, .y, .z, the constructor, and various methods. And the nice thing about these method descriptions is they often have a sample of code to show you the use of this particular tool. So here's the vector-3 cross product between side 1 and side 2, and then it normalized. So that's all very cool and makes life easy. And a lot of the tools that we need to do trigonometry in our Unity world is all prepared for us. So let's go on to the world's simplest controller. And in this simple controller, I'm going to access two of the axes. Get axis horizontal, which is the left and right arrow keys in the A and D key, and the vertical axis, which is the up and down arrow keys or the W and S keys. And here in this little simple program, I'm just going to set the position of my transform to be 5 times the vector H, a half, and V. So this is going to take the values of my two axes and kind of move my character to those positions. Now, the axes go from -1 to +1. So a left arrow pressed will go to -1, a right arrow pressed will go to +1, and if I release the keys, it goes back to 0. And it doesn't do it instantaneously, which is kind of what makes this nice, in that if I press the arrow keys, it goes gradually over to the right. And if I press the up and down arrow key, it goes gradually to the left. These can be looked at in the project settings under horizontal and vertical. Here it says it's left and right arrow key and A and D key. And one nice thing is the gravity and sensitivity, which is how rapidly it goes to the ±1 value and how rapidly it goes back to 0 again. So we have a lot of capability of tuning the behavior of our input axes here with the input manager. So let's look at this little program here. Again, pressing one or the other of the arrow keys. The other thing about axes is you can press 2 at the same time. So here I'm getting movement along the diagonals as I press 2 arrow keys at the same time. Moving on to maybe the next most simple controller, I'm now going to use a transform.translate function that takes X, Y, and Z values that I'm going to move my transform by that amount. So this is going to be cumulative in the sense that each update, it's going to move it further and further and further. And if I do this one, what I'll see is that rather quickly, my object moves quite fast. And that's because once the axis is at its ±1 value, it's now moving this by 1 meter per frame. And I'm getting something like 60 frames per second, so it's moving quite fast. And that's a problem. So with regards to the input class, we have the input axis. And besides the horizontal and vertical that are mapped to the W, A, S, and D and the arrow keys, there's also a mouse X and a mouse Y that is mapped to the mouse delta, how much it's moving up and down. This is the X, this is the Y. And then there are Fire 1, Fire 2, and Fire 3 buttons that map to the left control, Alt, and Command, as well as the 3 mouse buttons. Left mouse is 0, left mouse is Fire 1, right mouse is Fire 2, and I believe center mouse is Fire 3. You can see all of these and what they're set for in the input manager. And you can define your own axis in the input manager. They're easy to define. So it's recommended that if you're using input to control movement, that you should use an axis. Axes give you smooth and configurable input. It gradually goes from 0 to -1 or +1. How fast it goes there is settable in the input manager. If you have events that are triggered, like firing a bullet, that is a kind of a Boolean event. In this case, use the get button command instead. Don't use this for movement, but use it for events. There's also a get key that is kind of like get button is for the mouse and control option command. But there's also a get key that accesses any key on the keyboard. Another thing to note about the input is that the input flags aren't reset until the update function. And this means you should do all your input calls in an update function, not in a fixed update, and presumably not in a late update function. We'll see those later. So other things from the input class, there's also a read-only mouse position. This tells you where the mouse is at all times. It's not something you have to query, it's just always available. There's the any key that we've seen that returns a true if any key on the keyboard is pressed. The axes, as I mentioned, the button. There are other varieties of the get button. There's get button down, which returns a true at the moment the button is pressed, and there's a get mouse button up that returns a true at the moment the button is released. And of course, the get button itself is just true whenever the button is down. The analogous get key and get key down and get key up return true when the specific key is held down, is pressed at the moment it's pressed, or at the moment it's released. And with the get key, we'll select the key code that represents the key we want. Something like .r is the R key. So moving on to the world's simplest controller, version B, now I have an exposed variable, public float speed, a value of 5. And in my update, I'm going to catch in these two floats, x and z, the horizontal axis and the vertical axis, scaled by this public float speed, and both of them multiplied by time.delta time. Time.delta time is the time of the last frame, how long it took to render the last frame. And so it's kind of a measure of the frame rate of your game. And by multiplying this small fraction of a second times this speed, and then doing that movement every frame, I'm going to have the object move at a fixed speed of 5 meters per second, regardless what the frame rate is. If the frame rate is slowed down, time delta time will be bigger, and it'll still move 5 meters per second. This exposed variable speed is now kind of a tuning parameter that I can use to adjust how I want my object to behave. So here now with its default value of 5, we're moving 5 meters per second in the different directions. We're moving 5 meters per second. But I have this tuning parameter. If I want to set this up to 20 so that my character moves a lot faster, now my character moves faster. So I have this controlling parameter that I can use to set the speed of my character. The time class has, in addition to time.delta time that we use to enforce these constant rates, we also have time.time, which is the time since the beginning of the game. We have time.fixed time, which is the physics time step. And we have time.time scale, which is an interesting one. That's how fast time flows in the game. By default, it's 1 normal time. But if we set this to 0.5, the speed is 2 times slower, half as fast. I'm going to pause right here and come back the next time and start to look at the transform class. So I'll stop sharing and I'm going to end recording and I'll see you in class. Bye.